here we are looking at tests of dependence between two data sets, or more technically tests for independence. We are going to make the null hypothesis that there's no relationship between two data sets, and then we're going to look for evidence that actually something more interesting is happening in our sample, and that is there's evidence there is a relationship between two data sets. Now we could come at this from a parametric perspective where we purely test the correlation coefficient and we use the properties of how the sample correlation coefficient behaves around a true correlation coefficient. Very much like the hypothesis testing we did for a single mean when we're thinking about how x bar bounces around mu using the central limit theorem. But we can also approach this in non-parametric ways. We can test rank correlation. So instead of thinking about our correlation coefficient based on values of data, which gets the formal name the Pearson correlation coefficient, just in case you see that. If anyone ever says Pearson correlation, they just mean our usual correlation coefficient that we've already calculated from covariance using values. If we don't like using those values, usually because we're worried about outliers in the data, or usually simply because we want to do some more tests to see if we can confirm, or if you like, get more evidence that there's a relationship between two data sets, we might look at the ranks of observations, see if the first observation in data set A is occurring at the same time as the highest observation. When I say first, I mean the highest observation in data set B. That's the sort of thing we're doing with rank correlation, not basing it on values, but ranks of observations in their sample in terms of their size. And also we're going to look at contingency tables for categorical data. So here we're going to be counting the number of times we see a certain attribute in our data, like counting the number of times we see tall people, medium height people, short people, and see if we, and also count how many times we see high income, medium income, low income, and then we can test for us to see if there's a relationship between height and income. Okay, so let's start off with a parametric test of correlation. Now this is the first test here is a parametric test. It's testing the Pearson correlation coefficient. It's our old friend. It's the correlation coefficient derived from the values in our data by taking covariance and standardizing it. So we know all about this correlation coefficient. The sample correlation coefficient is given the letter R, and that is a random variable. It bounces around depending on what sample we look at, very much like the way x bar bounces around depending on what sample we look at. The crucial thing is that this sample correlation calculated from our sample is an estimate for the true population correlation, which is often getting the Greek letter rho here. That's a Greek R. All right, so it's a Greek R. As always, blue parameters get the Greek letters, and red sample statistics get our common letters. All right. So the question becomes here: we're going to do a hypothesis test. The classic hypotheses are that, and actually this is the hypothesis for this test, is what we're always assuming. The null is that the true correlation coefficient is 0, so there's no relationship between the two data sets that we're looking at, and the alternative hypothesis test is I should say, in this test is therefore the true correlation is non-zero, which is exciting. So there's the dull null with nothing in it, and there's the exciting alternative where we say there is a relationship and it's either positive or negative, and it's not just noise. So the main question here, like with our tests in the previous section, the main question here is how do we calculate our test statistic? Remember, your test statistic is a distance, all right? It's the number of standard errors you are away from a hypothesized value, in this case 0. So what you're looking at here, you know generally what you're looking at is the sample correlation coefficient, which is little r, right? Anything that comes from a sample, you know for these videos I've drawn it as red, and then anything to do with the population I've drawn it as blue, just to really put some color on what we're doing. So r, the distance that is away from, this test statistic is going to represent the distance that your observed r is away from your hypothesized value of 0, all right? We are hypothesizing a value of 0 in terms of the standard error of the sample correlation coefficient. Now, just remember, the standard error of a sample statistic is just its dispersion. That's just the volatility or the dispersion of your sample correlation coefficient. It's how widely dispersed it is around the true correlation coefficient row. All right. So look, r minus 0 on the top, that just stays at r, that's fine. And then your standard error, you're just going to have to take this from statistics. When we divide through by the standard error, that's how we get the rest of this term here. When we divide through by the standard error, it turns out it's the same thing as multiplying through by the root of n minus 2 and then dividing through by the root of 1 minus r squared. Now that's related to the standard error of the sample correlation coefficient, and it's one of those things that comes out of a level of statistics that actually we're not doing. We're applying it, but we're not deriving it. So you're just going to have to take this one on board. I think intuitively we can help. You know, there's n minus 2 degrees of freedom here in our two data sets, right? And we're collecting pairs of data here. So we're looking at x1, y1, right? When that's our first, if you like, observation. That's our first pair, x2, y2. And we get overall, we get x2 up to xn, xn, yn. We've got n pairs. So that's our overall level of degrees of freedom in terms of where randomness can come from. However, in our model, when we're thinking about correlation, actually to derive a correlation, we base it on covariance. And to calculate covariance, we do fix y bar and we do fix x bar. So by fixing those two sample means in our calculation of the covariance, in order to get to correlation here, we have lost 2 degrees of freedom. Because remember, these sample means should really be free. So there's us losing 2 degrees of freedom there. In other words, 2 of our data points are not random. They must take the value which sets x bar equal to the value we've used in our analysis and y bar equal to the value that we've used in our analysis. You're used to seeing, of course, axes flipped around here. Don't forget, I'm just drawing the x-axis is here, so the average x is like here. If we've got data like this, all right, the average x is here, and this is the y-axis. So this would be your average y if the data is distributed like that. This is what's called a scatter plot. More on that when we get into regression in the next reading. Okay. So we've got n minus 2 degrees of freedom. So it's no surprise to see an n minus 2 popping up when we're doing our statistics here. All right, that's part of the equation. And it goes on the top, and it's natural that it goes on the top, right? Because with more data, we can be more confident about our estimation. And so for a given r, we can say we're further away from a hypothesized value of 0. You know, if you take less data, you can be less confident that it's not just noise. All right, if you take more data, you're confident it's not just noise. And therefore, for a given sample statistic r, you actually you're a longer way away. Remember, more data biases down the standard error and increases up your distance away from the hypothesized value. So that's happening there explicitly. More n, more data, bigger numerator. And by the way, the bigger your r squared is in both positive and negative terms, because when you square it, it loses its sign. The smaller this denominator comes and the bigger your distance becomes as well. So if you can just remember n minus 2 and 1 minus r squared. By the way, the square root, of course, the square rooting comes from the fact that the standard error is a dispersion in volatility terms. All right, so volatility, of course, is the square root of the variance. So if you know that because there's a standard error involved here, there's going to be a square root sign, and it's both on the top and the bottom here. There's really just one square rooting going on, but it's happening on both the top and the bottom. You're going to have to remember this. The higher the n, the bigger the distance. The higher the r squared in both positive and negative terms, the lower this denominator, and therefore the bigger the distance. Okay. What's important is that you take that on board intuitively, and you commit the right amount of memory to it, and then you can use it. So let's use it. Here's a CFA Institute example. The exhibit below shows the sample correlations between monthly returns for 4 different mutual funds. So this here is a correlation matrix for funds 1 to 4. You can see they appear on as rows, and they appear as columns as well. And just to read it, this number here is the correlation of fund 2 versus fund 1. Okay. Test the null hypothesis that the correlation of fund 3 and 4 is equal to 0. That's always the null here. All right, that their correlation is equal to 0. In other words, there's no relationship. When we reject that, we find something interesting. So what's the sample correlation coefficient from our data? 3 and 4, that would be fund 3 versus fund 4. So we're going to have to go down here actually. They've only given us half the correlation matrix because it is symmetrical. So we'll go down here, we'll look at 4 versus 3. All right, it's this one here, 0.3102. So that's a big correlation, but is it big enough? You know, is it statistically significant? I mean, 0.3 usually is, but let's take a look. We're going to use 5% significance, same idea as when we're discussing hypothesis testing in the previous slide. And you're told, so that we don't mess around, you're told, this is a t-test by the way, with n minus 2 degrees of freedom. All right, this is going to be a t-test, but you're helpfully told that the relevant t-statistic, remember 2 will do when you're calculating 95% two-tailed. This is 95% confidence two-tailed, 2 will do. It turns out the exact figure is, well, it's about 2. So let's calculate our sample statistic. We know what our null hypothesis and our alternative hypotheses are going to be. We drew them up earlier. The null is dull, that there's nothing there. True correlation is 0. The alternative is that true correlation is non-zero, which is exciting. Let's calculate your t-stat, which is going to be R, the observed samples correlation statistic, 0.3102. That's R, that's coming from the table. All right, that's the R we're testing, 0.3102. Then we're going to multiply through by, remember, the square root of n minus 2. It's 2 data sets, so 2 dimensions. So we're losing 2 degrees of freedom when we fix those 2 sample means, essentially x bar, y bar. So 36. Now, where did we get that 36 for n from? Did we skip over that? We're looking here. This is quite, well, it's quite a common trick to say we're looking at 3 years worth of monthly data, but actually they've been more explicit there, and they just said, look, there's 36 months. So there's your n, 36. Okay, 36 observations. 36 minus 2 is 34, of course. And then underneath here, notice you only need r and n, and you can calculate the whole thing because underneath there you've got square root of 1 minus r squared. Okay, so take your time on the calculator. The keystrokes I would use here, there's quite a bit of junk going on the bottom. So I'll start on the bottom here, and I'll start with the fiddliest thing, and that is squaring this 0.3102. So I'm going to go always start with the nastiest area of an equation, the nastiest area where there's the most brackets and roots and squares and powers and things. So 0.3102, and the denominator is nastier than the numerator, by the way, so squared. There you go, that's that number there. Now my little trick here would be to negate it, turn it negative like that, hit plus minus, and then add 1. That's a neat little trick to speed you up a bit. All right, so what I've got now is 1 minus 0.3102 squared. Then I can root that whole thing on the bottom. That's great, that's what's on the bottom. Just hit the root sign. Then what I can do is put it on the bottom by hitting 1 over. Right, so now it's on the bottom. Right, now I can multiply by 0.3102. So multiply by 0.3102. And I'm going to hit equals there. Now I've got this, all this stuff out. I've got that and I've got that. All right, now all I need to do is multiply by the root of 34. So I'll multiply by 34 root, okay, equals, and there you go, 1.903. So that's, you know, you might find that useful. That might speed you up a little bit when you look at the calculator, okay? All right, so make the decision. What have we got? We've got a test stat that's 1.903. Don't forget what that is. That's the number of standard errors that R is away from a hypothesized value of 0. Is that far enough? Well, the critical value was 2 will do, right? It's pretty close, but it's not good enough. So we failed to reject the null, that actually the true relationship is 0. I said the correlation coefficient was big earlier on, but it isn't big enough to rule out with 95% confidence that it is just a little bit of noise in the data. All right, now if you're worried about outliers in your data, big positive values, big negative values, biasing the Pearson correlation coefficient, which is what we are testing here, then you might turn to ranks. This is a non-parametric test. You're testing the ranks of the 2 samples against each other. And obviously, if you see the highest observation in sample 1 when you're seeing the highest observation in sample 2, and you see the lowest observation in sample 1 and sample 2 at the same time, obviously they're related, but you're not looking at values, you're looking at the ranks of the data that you're observing in each sample. So you do need samples of similar sizes, the same size, right? The sizes that you're looking at are n again. And what you're going to do is you're going to tally up the difference between the 2 ranks. That's what D is here. you're actually going to tally up the sum. That's sigma there is the sum of the distances squared. And that sum of distances squared in ranks is going to be adjusted for how it behaves and subtracted from 1. And the idea is if this sum of distances is big, then your ranks are very different and your correlation comes down from 100% and can even go negative and go to -1 if the differences are as big as they could possibly be. Now this is another formula that stands on the shoulders of statistical theory and indeed mathematical counting that we don't actually do in the CFA curriculum. What's important is that you can apply this formula. One of the things I'm just going to do to give you a bit of context here is to just point out that this rank, it's called the Spearman rank correlation coefficient, it does still sit between +1 and -1. And what we might want to do just to get a bit comfortable with this thing, because it is quite ugly when we first meet it, and then we'll apply it to get familiar with it. What we might want to do is think about what happens when we have data that's perfectly in line, perfectly correlated from a ranks perspective. Let's say we've got 3 data points in each sample, so n is 3. And let's say that when we look at the first data set, let's call it X, when we see the highest one, we're also seeing, in terms of ranks, right? Ranks of data. When we see the highest, the biggest one in X, we see the biggest one in Y at the same time. And, when we see the second one in X, we see the second one in Y. And when we see the lowest one in X, we see the lowest one in Y. Now, trivially, the distances here are all 0. 1 minus 1 is 0. 2 minus 2 is 0. 3 minus 3 is 0. And so the sum of your d squareds, if I square those, you still get zeros. Sum of d squareds is 0. And so this thing all collapses and you get your correlation is 1. And that's what you want when there's no difference in ranks. You might want to think about what happens when you have the biggest difference in ranks that you possibly can. So you want a correlation of -1 here, don't you, when you're seeing at the same time the highest observation in X but the lowest observation in Y. You see the middle observations together, that's fine. But when you see the lowest observation in X, you see the highest observation in Y. When you think about the distances here, squared, that's just not trivially 0. 1 minus 3 is -2. Square it, you'll get 4. Right? 2 minus 2 is 0. 0 squared is 0. 3 minus 1 is 2. 2 squared is 4. Add up the sum of the d's squared and you get 4 plus 0 plus 4, which is 8. Now, remember this, we really want in this scenario, we really want to see a correlation coefficient of -1, don't we? Because they're perfectly moving against each other. I know it's small data, but they are perfectly moving against each other. Now, what you'll notice is with an n of 3, this term on the bottom here, n squared minus 1, that would be 3 lots of 3 squared minus 1. That is 3 lots of 9 minus 1, because 3 squared is 9. 9 minus 1 is 8. So you've got 24 here. So the n on the bottom, let's just clear this up a bit because it's got a bit messy. Let's just clear this up a bit. On the bottom, when we've got perfect negative correlation, which you have here in ranks, on the bottom you get 24, right? On the top you've got 6 lots of, what's this, 8, all right? The sum of d squared is 8. 6 eighths, of course, are 48. And on the bottom, we've got 24. So what are we taking off? We're taking off 2. And 1 minus 2 is -1, which is exactly what you want. So it's rather arcane and feels like it's appearing from nowhere. But this 6 and this n times n squared minus 1, what it's really doing is it's adjusting the sum of d squareds such that it's a number that can sit essentially between 0 and 2. All right? And it's at 0, when all of the d squareds are 0, trivially, and gives you a correlation coefficient +1. It's actually at 2 when the d squareds are as big as they possibly can be. It involves a little bit of mathematical calculating and summation, but that's what the 6 and the n times n squared minus 1 is actually doing. It's just adjusting your sigma d squared such that it sits between 0, when you have perfect correlation, perfect relationship between ranks, and 2, when you have the biggest distance between ranks as possible. Now, with that in mind, you're just going to have to commit your memory to this and remember the shape that it takes, because we don't look into the mathematics of the summation at CFA 1, but we do use it. And this does turn out to be a t-test. If you've got enough data, it does turn out to be a t-test with enough data is greater than 30 data points. Use a t-table with n-2 degrees of freedom. You know, practically for the exam, you need to start thinking that when you're doing correlation, you've got two data sets and there's two dimensions. So in terms of randomness, you can get randomness from all of your data points apart from two of them, essentially. Because the way to think about it is you're fixing two dimensions to do your analysis. So let's apply this. Here we've got two samples, sample from data from distribution A and a sample from distribution B. And they are pairs, by the way. At time 1, we're observing this pair. They're doing it at the same time. And n is 52 here because that's the number of pairs we have. And what's more important than the values is the ranking of the values. So 12% is the third highest observation in the sample from A. Minus 2% is the 36th ranking observation. ... We're not going to show all the observations here. 0 is right. Well, it's not right in the middle of the data, but it's in the middle of the data. 28th ranking out of 52. And similarly, we've got rankings for B. So return of 3 and 4, 10th and 12th. The return of 6 is 18th in the data. So it's these two columns which are important. We get our DIs by taking the first rank, subtracting the second rank. Minus 7, 36 minus 12 is 24, 28 minus 18 is 10. Some people worry about, like, do you do A minus B or B minus A? It actually doesn't matter. It's all symmetrical, and the total number of differences in ranks has to add up to be 0, essentially, when you include the signs. That's why we square them, to ignore that. So it is all symmetrical. You know, if you've got a big difference in ranks, then that needs to be made up elsewhere. That might not be immediately obvious, but you just trust that. It doesn't matter whether you do A minus B or B minus A, because it all nets out to 0 in the end anyway. That's why we square it. Okay. So the sum of these, so 7 minus 7 squared is 49. Square, 24 squared is 576. 10 squared obviously is 100. Sum those up, you get 6,533. So you obviously won't be doing that in the exam, but you may be given that as an output to a regression analysis. Perform a test of independence on the data with 5% significance. Okay, so this is how we get our sample R. We use the formula for the Spearman rank correlation coefficient. 1 minus 6 lots of sigma d squared over n lots of n squared minus 1. So this junk here, that ugly stuff there, that is what that number is, 6533, okay? All you need to do is take 6533, multiply it by 6. Remember, this is just an adjustment to make the squared differences in ranks behave between 0 and plus 2, all right, which is what we want them to do. And then we divide by n lots of n squared minus 1. Once again, not necessarily a trivial thing to do on the calculator. So to speed you up a bit, I'll just, for me, don't forget you've got 1 minus this thing. So what I'm going to do is get stuck into the second thing, which is uglier. Get on the bottom, which is the ugly bit. Get inside the brackets. The ugliest bit I can find is 52 squared. So 52 squared minus 1 gives me that bracket on the bottom, 2703, times by 52. That's fine. Then I've got the whole of the thing on the bottom. All right, the whole of the thing on the bottom there is 140,000. I can put it on the bottom of a fraction by flipping it over, 1 over, very small number. But don't worry, we'll multiply it by some big things on the top. So multiply by 6, that's multiplying by 6, and then multiply by 6,533. So multiply by 6,533. Hopefully we've got, yeah, okay, that's a non sort of, it's a non-tiny number, 0.27. Now to take that off of 1, what I do is I negate it and add 1. That's a nice little trick to speed you up. Negate it and add 1, and you get 0.72, which is what you're looking at here. Okay, so that looks pretty big to me. Sample correlation coefficient of 0.72. That's huge. But just to go through the motions of showing that that is significantly different from 0, we now perform a t-test on the R we've just calculated. Okay, we've got enough data. Perform a test of independence on the data with 5% significance. All right, we go to a t-table. Degrees of freedom of 50 here. Well, I say we've got enough data. That's because N is 52. All right, remember that from before. There it is, N is 52. So N minus 2, which is our degrees of freedom, that will be 50. We can look at a T table. This must be a T table. And we're looking for, it's a two-tailed test, remember. R is 0, and there's two tails, could be greater than, or less than 0. So it's two tails. The area in the tail that we're interested in is that 2.01. All right, 2.5% in each tail. Okay, so that 5% is split across two tails. And we calculate the test stat same as before. All right, sample correlation coefficient of 0.72 times square root of 50 divided by square root of 1 minus RR squared. I did do the keystrokes for this on the earlier one. Have a look at that if you want to follow the keystrokes. We get a whopping T-stat of 7.34. And, 2 will do 95% two-tailed. It's going to be around about 2, whatever it is. You could have just calculated. This is my recommendation, actually. Calculate the T-stat first. And if that distance is like 3, even if it's sort of greater than... If it's greater than 3, I can't think of any scenario where you'd then go and spend time looking up a critical value with a t-test and go, oh, look at that. We're not going to reject. You're always rejecting when your test statistic, your test distance is greater than 3. So 7 is whopping. It's pretty much impossible under null conditions. Therefore, we reject the null hypothesis. Okay, the final topic in this module is contingency tables. So contingency tables are a very practical, straightforward, really, tool used by statisticians when we've got categorical data. So categorical data is where you count the number of times you observe a certain category. Okay, what you're doing is, we'll look at this through an example. What you're doing is you're looking for a relationship between two features. So for example, dividend yield being low, medium or high versus earnings growth being low, medium or high. You're looking for a relationship between those two features. And you're taking a sample of size 324, and then according to your definitions, you're just counting. These are actual observations in the table here. You're just counting the number of times that you observe for example, here you've got low earnings growth, low dividend yield. Here you've got low earnings growth, medium dividend yield. This one over here is high earnings growth, high dividend yield. These are actual observations in the table here, labeled as O. You can see there's 9 cells here, as it's called. Now, we should be used to the dull null not being very interesting. The dull null here is that the data is independent. There's no relationship. Okay. And the alternative is exciting. And that is that it's not purely platonic. There's something going on. All right. Which is exciting. Right. So the question becomes, what would we expect under null conditions? Under null conditions, when there's no relationship between dividend yield and earnings growth, what would we expect to see in this table? So the idea is, if there's no relationship between earnings growth and dividend yield, each row would look the same as they're split across dividend yields, different levels of dividend yield. Each row would be the same because there's no difference between a low earnings growth company and a high earnings growth company when you look at their split across dividend yield. So another way to interpret that is to say that what we expect to see in each cell is, for the first row, take the total in the row, 123, and you don't expect to see anything other than, if there's no relationship, you don't expect the number in this cell to be driven by anything other than how many low dividend companies there are as a proportion of the total number of companies we've looked at. So if you take that 123 and you multiply up by the column total as a fraction of the total, that is what you expect to see in that cell. All right, if all the rows are the same and they're just driven by the proportion of low dividend yield companies as a fraction of the whole. Okay, and every row is split like that. So there's no relationship. There's no difference between a low earnings growth company, how it's split across dividend yield, and a high earnings growth company, how it's split across dividend yield. Now, if I calculate this number, I get 123 multiplied by 119, divide 324, and I get 45. So to the nearest whole number, I would expect to see 45 in that cell. Okay, where's my cursor? There it is. All right, so I expect to see 45 in that cell. I've actually only seen my red observation was only 28. So that's a lot lower. What you've actually seen is a lot lower. It's lower by 17. So is that a big deal? Well, what you do is you take your observations. So that's what we've just done. We've looked at, let's just clear. For every cell, you're going to do this green expectation. All right, so I won't calculate them, but for example, in this cell here, the expected value under the assumption, under null conditions of no relationship, would be the row value 1, 2, 3, and it would just be split according to columns. 110 out of 324. All right, so whatever that number is. This one, for example, given that I picked that one out earlier, that number there, whilst we've actually observed 14, what we'd expect to see in that cell would be row total of 88 split according to the general proportion of high dividend yield companies, 95 out of the 324 total. Right, that's what we'd expect to see there. For what it's worth, 88, I'll calculate that one, times 95, divide 324. We'd actually expect to see 25 there, all right, or 26 when I round. And so, once again, massively underweight there, the high earnings growth, high dividend. We're seeing a lot fewer than we would expect under null conditions. So how can we quantify this from a statistical perspective, the difference between our expected numbers in the table and our red observed numbers? Well, what you do is you take the difference between what's actually been observed and what was expected in each cell. So the difference between the expected value calculated using that little formula and what you actually observed, what's in the table. Square the difference. So 45, so you'd actually technically with that first cell here, it would be 28 seen versus 45 expected. That would be minus 17, but then you square it to remove signs. We should be used to doing that for distances by now. All right, and then we think about how big that square is as a proportion of what we expected for the cell. All right, so for the first cell, I'll just do it for the first cell. In fact, we're going to do an example in a moment, so I won't duplicate. But if you do that for every cell and then you sum that up, what you actually get is a chi-square statistic. Nice and easy to remember because you're dealing with squared distances. With degrees of freedom, how many degrees of freedom have we got? Well, we've actually got degrees of freedom here. Think about the table. How many data points have we got in the table? There's number of rows times number of columns, right? But there's 2 dimensions as well. And just like when we lose a degree of freedom in each dimension when we fix a mean, we have lost a degree of freedom in each dimension here. But be careful. It's not RC minus 2. It's actually, we're really looking at the number of rows and columns in terms of our degrees of freedom, because that's what we're using really in our stats. So it's R minus 1 times C minus 1. That's our number of degrees of freedom. We've lost 1 degree of freedom from the number of rows, because if you like, that's 1 dimension. And we've lost the 1 degree of freedom from the number of columns, because that's 1 dimension. In this particular case, we've got 3 rows and we've got 3 columns, so the degrees of freedom would be 2 times 2, which is 4, of course. Okay, so you're looking at a chi-square statistic with degrees of freedom 4 in that particular case. All right, with degrees of freedom, it's not a statistics course, so it always feels a bit ethereal, but hopefully you're carrying through earlier discussions from earlier modules where I always describe, you think about the dimensions that you've got and then subtract 1, and that's coming through here in a kind of a tabular form. Number of rows minus 1 times the number of columns minus 1. That's the area that we're looking at in terms of how free it is. All right, let's have a look at a CFAI example on this. Consider, if you will, the contingency table below which classifies 500, so that should be the number in the bottom right. Yes, it is. Randomly selected companies on the basis of 2 ESG dimensions. So your 2 dimensions here are governance rating and environmental rating. The question is, really, companies with good governance ratings, do they tend to have good environmental ratings, or vice versa even? Is there any read-through, say, from good governance rating to good environmental rating, or vice versa? We don't specify causality here. We're really just looking for a relationship. So we are going to do a test using the chi-square statistic. There will be a significance level of 5%, playing the same role as before. All right, so let's get on and do this. The first thing to do is to calculate your expected values for each cell. Remember, what's in the table are the observed values for each cell, your O's if you like. What we need to do is calculate your expected values for each cell, and that's done using the formula. Let's remind ourselves the formula is your expected value is the row total that you're in, and the way I think about it is you're breaking that up in the same proportion as the column total out of the total, right, grand sum. All right, Total. So the expected frequency for cell 1, that's row 1 and column 1, is going to be the row total, which is 80. We're going to split that according to how much we see in the overall column, 1 out of the proportion of 500. So we should be seeing here 80 times 155 divided by 500. There you go. 24.8. Okay, and then similarly for cell 1, 2, that's row 1, column 2, we expect to see it would be 80 split by 230 out of 500. All right, that's great. And then hopefully it's relatively straightforward. Row 2, column 1, we've changed rows, so we're going to be splitting this 260 from row 2 out by 155 over 500. That's what we'd expect to see under null conditions. So that's completed the table. This is our expectations, all right? These are our expectations, our E's. So you've got your O's in the original table. You've got your E's in those in that expected table. Now you can calculate your chi-square statistic, all right? So the scaled square deviation, which is what, the component of the chi-square statistic coming from the first cell, would be an actual observation of 35. That was in the original table. All right, minus the expected value of 24.8. We will go to one decimal place here. Don't have to round it to a whole number. Square that and divide by E. All right, and that's 4.195. Similarly, you get an observation of 40 versus an expected value of 36.8 for cell 1, 2. That's this one here. And you get a squared deviation of 0.004 for cell 2, 1. And that's because we actually observed 80 when we expected to see 80.6. So you square that's very small, particularly as a proportion of the 80.6 that you expected. Okay, so this does look like you're trudging around, and I'm sure a lot of you are sitting there thinking, would I have to do this in a question? The answer is probably not the whole thing, not for 9 observations, but you need to know the process. You could be asked about the process or to do one of these. What would be a very, I think, fair exam question would be to complete a table like this or to calculate one of these cells. If you add up all of these scaled squared deviations, you will get to 35.74. So that 35.74 we've just calculated as a chi-square statistic, and the degrees of freedom are, you'll remember, number of rows minus 1 times number of columns minus 1. So number of rows is 3, number of columns is 3. That gives us degrees of freedom of 4, like we said earlier. Okay, so what you do now to get your critical chi-squared, we've calculated our test statistic, 35.74. On the previous slide, what you do to get your critical value is you turn to a chi-squared table, and you look at the 4 degrees of freedom row. And the question is, with 5% significance, which we were told at the start of the test, how much have we got in the tail? Well, this is a one-tailed test. There's a chi-square distribution with 4 degrees of freedom. There's 5% significance in one tail. Why is it one-tailed? It's because our statistic is a squared distance away from what we expect. We'd only ever reject what we expect, the null conditions, if that squared distance is high. We wouldn't reject if that squared distance is low. So there's a one-tailed test. You need to remember that. And there's only one. We can only reject when things are big, when the test stat is big. So we're looking at all the 5% in the right-hand tail. We've been given the probabilities in the right-hand tail here. There's 5%. And therefore, the statistic that we're interested in is 9.49. So we've got a test stat of 35.74. The critical value from the table. Remember, the critical values always come from tables. Test statistics always come from a little calculation. We've got a greater, much greater. We're way into the rejection zone here. So we reject the null, that there's no relationship between the two features. And we conclude that there is a relationship between environmental rating and governance rating. Now, we just did that test. We almost did it blind. We kind of did it without just looking at the data. That's something I'd always recommend, is look at the data. Now go right back to the start, look at the data. Generally speaking, you haven't got many poor governance companies that are progressive, which is good, presumably, from an environmental perspective. And generally speaking, the other low numbers, you've got to be careful making sweeping judgments here, but this looks to be pretty low as well. Maybe. All right. So maybe sometimes you can look at the data and see the relationship. But what where the mass of this is, if you like, of this table is here. Average implies average. And when you're progressive, you're good. You tend to be, there's more good progressive firms that are, progressive in both areas. And poor as well, that tends to be quite big as well. So there does, we have to do the stats. You can't look at it and have an opinion about this data. You have to do the stats. But I would wager that what we're seeing here is that there is a relationship. Companies that are good environmentally tend to be good from a governance perspective as well. Maybe you can see that from your distances, relative to what you expect. We saw 35 here, top left, 5 top right. So just based on what we expect, there was 35 here, right? That's what we saw, which is more than what was expected if they're independent. There was only 5 here. So if you're a good environmental company, chances are you're not a poor, you haven't got a poor governance rating, you've actually got good governance rating as well. So you can see the relationship coming through if you know what to look for in the data. But so don't necessarily always go blind into this. We have rejected with a very low p-value here by the looks of things. In other words, we've seen something very unlikely under null conditions. So you might be able to see that from the data first off without any arcane statistics. All right, well, that concludes this relatively short module. There's 3 major tests here: Pearson correlation, Spearman rank correlation, and the contingency tables. Make sure you can talk about them. You don't have to do them all yourself like we've done in the master classes, but you have to know the process and know what goes in, interpret what comes out, and do each individual stage should you be asked to in a single multi-choice question.